And welcome everyone to Scott Freitas' thesis proposal for his ML PhD dissertation. And we have a thesis committee member, Professor Li and Suzanne Kumar, and also myself as an advisor. And as we mentioned, so we are recording the presentation portion of the dissertation talk. And if you have questions, so I encourage to type them out in the chat window. We'll leave the question until the end of the presentation, where we'll have dedicated time for that. And so without further ado, so Scott, please take it away.
Okay, thank you very much. Let me slide shared here. Actually, let me share the other screen here so I can look at the camera when I'm talking. Okay.
Yeah, looks good.
That's good. Great. Okay, thank you everyone for being here today. I'm Scott Freitas, and I'll be presenting my ML PhD thesis proposal, which is developing robust models, algorithms, databases, and tools with applications to cybersecurity and healthcare. And a special thanks to my committee who's here today, Dee Yang, Suzanne Kumar, and Polo Chow, my advisor. So first off, let's start by talking about how machine learning is all around us right now. It ranges from cybersecurity to autonomous vehicles, to infrastructure monitoring, social media news feeds, and health informatics, and also things like spelling and text prediction. The real thing is that machine learning is all around us in things that we're doing currently. Unfortunately, bad guys also realize this and use these machine learning systems to disrupt our daily lives. We often see things on the news like it's disturbingly easy to trick AI into doing something deadly. This could be for self-driving cars, medicine, military systems. We see how ransomware is costing millions of dollars per year. And we can also see how cybersecurity attacks are hitting our power and utility grids. So this sort of emphasizes why we need robust machine learning. Essentially so we can detect and prevent attacks on our critical infrastructure, our self-driving cars, and our enterprise networks. In addition, we also want to improve our decision making, making these models robust to noise, also so we can identify weak points in them, and we can quantify our vulnerability to these kinds of attacks. Throughout my time here in the PhD program, I've worked with great people at Microsoft ATP, Intel, Amazon, and the Naval Air Warfare Center. And the one thing that I've really seen here is machine learning is transforming the public and private sector. And the question is, how do we protect it? So this brings us to why do we need robust machine learning? So for cybersecurity, this can be things like preventing backdoors. For autonomous vehicles, it's for safe driving. Infrastructure monitoring to prevent outages. Social media newsfeed to prevent pigeonholing. And health informatics for even saving lives. The key here, though, is that robust machine learning protects us. So this dissertation research mission here is to address large-scale societal problems in cybersecurity and healthcare through the lens of robust machine learning. And throughout this thesis, we're going to break this down into 4 different parts: tools, algorithms, databases, and models. So in part 1, tools, we begin by developing critically needed tools to help guide and assist researchers in navigating the complex field of graph robustness. And then in part 2, through our survey and the development of the Tiger toolbox in part 1, we find that network robustness research has primarily focused on the development of algorithms to study social networks and infrastructure networks, but has failed to look at key issues in cybersecurity. So in part 2 in algorithms, we take a first step to address this by studying robustness authentication graphs and enterprise networks to prevent lateral attacks. And then throughout part 2, we sort of focused on a post-breach adversarial detection and modeling scenario once an adversary is already on your network and what you can do about that. So part 3 of the thesis, our goal is to prevent lateral attacks altogether by creating new databases to enable the development of next-generation malware detection models. And finally, in part 4, we find that these models are actually very vulnerable to noise many times. And so essentially we want to develop robust models that can help prevent these attacks altogether. So let's begin by starting with part 1 here. developing tools to assist researchers navigating the complex field of graph robustness. And with this, we'll start with the Robustness Survey, and essentially a little bit of motivation for why we need robust tools. So the goal here is to democratize knowledge and equip users with the key tools they need to develop robust machine learning systems. So a few pieces of information here. So cyber attacks cost the U.S. economy up to $109 billion in 2016 alone. And robustness knowledge is generally currently scattered across many disparate fields in physics, mathematics, computer science, with no key thing bringing them all together. In addition, key data and libraries are often the possession of a few leading industry labs such as Google, Facebook, Microsoft, and bringing them together, making it open source for people is really crucial. So this brings us to the Robustness Survey, the first paper we'll discuss, titled Graph Formulating Robustness Survey. And this is a collaboration between myself, Dee, Srijan, Hong, and Polo. And we're currently planning to submit this to TKDE in 2021 in the next month here, which is a good top data mining journal. A little bit of overview here. So some highlights to take away from the survey essentially is that we spent time comparing about 85 high-impact and recent papers in the field of graph robustness. Essentially, that's what we can see here over on the figure on the right, where we break each paper into a row, and then each of the columns groups into what the paper studies essentially. So this could be robustness measures, which take time to measure the actual robustness of these graphs. So give you an idea for different kinds of connectivity patterns. And then in part 2 there, we see the attacks. So this tells you what kind of attacks these papers study on these networks. And finally, the third column we focus on is the defense. So that these papers focus on defense of these attacks, what kind of defenses they look at. And we'll go to each of these in a little more depth here. So as I previously mentioned, we had the robustness measures, the failure and attack scenarios, and the defense techniques. And this gives you more of a comprehensive overview of what this really means. So let's start at the top here with robustness measures, where we can summarize and compare 18 of the robustness measures in this paper. So these could be things like graph measures, which look at the statistical analysis of the graph itself, like the diameter, the average distance, its edge connectivity. And this can give you a measure of the graph robustness based on the topology of the graph itself. However, there's also things like the adjacency measures, which look at the spectral radius of the graph, spectral scaling, natural connectivity. And these are all based on the adjacency matrix itself. And then finally, people look at the Laplacian matrix when they look at graph robustness, looking at things like effective resistance, algebraic connectivity, or the number of spanning trees in the graph. And all these have different meanings when you measure graph robustness. In the second part of the survey, we look at failure scenarios. And we study various failure scenarios on different types of graph topologies. So things you might see in these kinds of attacks or failures is failure of a single node. And this could just be a random event, natural occurrence, or it could be something like a target attack on the right here, where people are really intentionally damaging specific nodes in the graph, or often in order to cause cascading failures. And this brings us to our middle point here, cascading failures, where basically when one node fails in the graph, this can result in a chain of nodes failing in the graph also. In order to prevent these kinds of things, we also want to look at the defense techniques. So we study a large variety of defense techniques in order to prevent these kinds of failure scenarios. This could be things like edge addition, where you're actually adding new physical connections to the graph topology. It could be edge rewiring, where you're rewiring existing edges throughout the graph in order to prevent these kinds of cascading failures from occurring. And finally, this also things include node monitoring. So you're monitoring critical nodes in the graph, typically with some sort of high centrality measure, in order to prevent these attacks from happening in the first place. A little bit of recap here. So in the survey paper itself, there was 5 major contributions of what we did. So the first off was the summary and comparison of 18 robustness measures, exploration of robustness measure applications to various scenarios like water distribution networks, electrical grids, and also along with the overview of different kinds of attack strategies and when they're effective, on what kind of graph topologies you'd see these attacks really do damage. And then finally, we also compared different kinds of network defense mechanisms in relation to the different attack strategies. And then finally, we wrapped up the survey doing a highlight of open problems and research directions for people to consider in the future. So throughout our time through the survey paper, we also found that basically there was a dearth of tools allowing people to analyze all these different critical and key components of graphs, which led to the impetus for Tiger, which is a robustness toolbox to evaluate graph vulnerability and robustness. And currently, we're also planning to submit this to CIKM. This work is largely done, and we'll submit this within the next couple of weeks. So a little bit of overview about Tiger itself here. So Tiger is a GPU-accelerated Python library and part of the NVIDIA Data Science Teaching Kit. And there's four major things which the toolbox allows us to do. First thing is to quantify network vulnerability and robustness. The second thing is to simulate a variety of network attacks, cascading failures, and spread of dissemination of entities. And then thirdly, we can augment a network structure to resist attacks and recover from failure. And then finally, we can regulate the dissemination of entities of network, such as virus and propaganda. So a little bit about the contributions of the Tiger toolbox itself. So there's five major things which we contribute through Tiger. The first thing is that this is the first actual open source Python toolbox that allow users to evaluate graph vulnerability and robustness. And secondly, we include 22 robustness measures with both original and fast approximate counterparts. We also include 17 failure and attack mechanisms, 15 defense strategies, and 4 network simulation techniques. So let's dive into a little bit of each of these different things, starting with the robustness measures. So we talked about earlier in the survey paper, there's different kinds of robustness measures based on the graph, the adjacency matrix, and the Laplacian matrix. This sort of shows how they break down in the toolbox. We include 9 graph measures along with 2 approximate variations, 5 adjacency matrix measures, and 3 Laplacian measures with 2 approximate fast counterparts. This gives you a high-level overview of the different kinds of robustness measures users could actually study when looking at these graphs. Secondly, we also have 17 different kinds of failure and attack mechanisms. And here on the right, we actually give an example of a node attack on a real water distribution network, which is called the Kentucky KYC water distribution network in this case. And here we're simulating an attack over 27 time steps. And this time steps is just each node is being attacked at one time step. So at step 0, we see the whole water distribution network is purple, meaning it's one giant connected component. We can see after 13 different node attacks, which is targeted in this case, we can see how the water distribution network is broken into 2 disconnected components, see how it's already beginning to fracture the network. By step 22, we can see that's fractured into 3 disconnected components. By step 27, it's actually 4 disconnected components, really hindering the operation of the network by this point. We also include 15 different defense techniques, and actually we show this one as an SIS, a susceptible infection model, on an Organ 1 autonomous system network, which is a router backbone network of the internet. And on top of this figure, we see what happens when the virus is already pervasive throughout the network. And basically our goal to see is what's the steady state after time. We can see after 1,000 steps, the virus remains endemic to the network, meaning we aren't able to get rid of it. So the key question is, how would that actually change when you're defending certain key nodes in the graph? So defending only 5 nodes in the graph, we can actually see that by step 1,000, the network has actually almost completely eradicated the virus. And this actually sort of demonstrates the key importance of how important good defense can be with something powerful and important as viruses on networks. And finally, also include different simulation techniques, some things we already talked about, such as entity dissemination, attacks, defenses. And this one's a little bit about cascading failures, which we show in the example below. So this is actually a US power grid when 4 substations are attacked. In step 1 on the left, we can see a normally operating graph or power distribution network, where essentially we've attacked 4 critical substations in it, which starts at the bottom. So these 4 substations at the bottom, and we can see in step 50 in the middle here how cascading failures actually happen. So when these 4 nodes at the bottom actually start to fail, it results in a chain of different nodes around them starting to fail. By step 70, we can see most of the network has actually collapsed. And this would be like a blackout scenario. Excuse me. So in summary, we just addressed part 1 of the survey or the dissertation. Now we'll move into part 2 of it, which is the algorithmic component. And this here, we're trying to identify and create algorithms that quantify network vulnerability to lateral attacks. So the impetus here is that we developed the tools in part 1, and essentially through this, we saw there was actually quite a bit of lacking of the tools needed for the cybersecurity domain. So this is an effort to develop different kinds of algorithms needed to actually protect critical enterprise networks. So essentially, through our survey and development at Tiger, we find that network robustness has yet to address these key issues in cybersecurity, and this observation motivated us to study robustness authentication graphs enterprise networks, leading us to D²M, dynamic defense and modeling adversarial movement in networks. This is a collaboration between myself, Andrew, Joshua, and Polo. And this work was done when I was at Microsoft 2 years ago. And this was submitted to and accepted to SDM 2020, top data mining conference. So let's talk a little bit about what this paper is about. So essentially, we're going to start with this figure here, which motivates the lateral movement attack chain. And this will sort of set up the whole problem which we're going to talk about. There's actually 6 steps here we're going to highlight. So the first is a pre-breach scenario where attacker in step 1 here is looking to penetrate the network. And so basically this could be like phishing, and basically once he's on the network, now his goal is to laterally move across it, explore it, and try to escalate his privileges. So he might move up to admin, then he might escalate to domain network admin, and then escalate further to the domain admin, laterally moving and escalating these privileges until he can compromise the domain controller itself. And once this domain control of the network has been compromised, essentially he has full access and control over the network, and he can begin to exfiltrate data at ease. And this is a very typical scenario we'd see when all of these different kinds of corporations, enterprises are continuously being compromised. And this is how they do it, and this is their goal. So this brings us to the defender's dilemma. So we want to actually defend against these kinds of lateral attacks and develop defense strategies and vulnerability analysis for these kinds of attacks. However, the problem is that there's sparse observable data on all these lateral attacks, largely due to ground truth partially uncovered through investigation. You can imagine it's actually hard to see all the different kinds of lateral attacks going on throughout the network. Incident reports are often withheld, and they're not shared across companies. And also, we cannot store network telemetry more than 6 months typically due to GDPR regulations. And finally, this is more of a tricky point, but attackers can actually operate as legitimate users on this network. So it's actually very hard to distinguish real lateral attacks from actual normal activity sometimes. So what's the solution? So our here, essentially, our goal is to develop these defense strategies, but we actually don't have this ground truth. So what can we do? So our idea is basically to simulate lateral attacks on these enterprise networks by developing realistic lateral attack environment, which we work with different Microsoft threat experts to actually come up with a simulation environment, allowing us to model multiple kinds of attack strategy you might see in the real world. And we also incorporate specific domain knowledge into the simulation environment to make it more realistic. So this brings us to the D²M framework itself. And it's really 3 major contributions, and we can talk about each part in this figure. So on the left, basically we have the network data itself, where we build the authentication graph. And using this network authentication graph data, this brings us to the simulation framework itself, which allows us to simulate the penetration of the network, the attack exploration, the actual compromise of these different kinds of components. And then part 2 and 3 on the right, our goal is basically using the simulation framework to actually be able to measure the vulnerability of the network to lateral attacks itself, and then further to identify these at-risk machines to monitor to help prevent these lateral attacks from happening. So let's move into a little bit more of the technical aspect. Let's talk about the authentication graph and domain knowledge and how this is actually going to get set up here. So the network activity forms a directed graph, G, and this is comprised of 2 different components. V, the set of network machines, and then E, the set of edges representing authentication activity between machines. We can think this is like remote logins from one machine to another. And these things happen quite frequently, and we collect those over a period of 30 days. And then for the domain knowledge itself, we can incorporate 3 different real mechanisms. First, the attacker can start on any machine in the network with a very low-level user credential, allowing to simulate different kinds of penetration on the network. We allow them to then explore and exploit the network, trying to laterally move, according to basically it could be like sort of random, with no knowledge of the network, or they can move a priori with some knowledge of the topology and move more informed strategies. And then finally, we simulate the exfiltration network by saying once they've compromised the domain controller, the simulation ends because essentially at that point, they can do whatever they need to on the network. So let's talk a little about attack strategies. We'll talk about one in this case, which is an uninformed strategy called random walk explore. So this means the attacker has no knowledge of what the network topology looks like, and once he's penetrated the network, he's now trying to move across the network laterally to escalate privileges. So with an 85% chance, we say the attacker uniformly selects a neighbor, which is a machine that he's remotely logged into previously from that machine, or a legitimate user has previously remotely logged into, I should say. And now he's using those prior remote logins to move across to a new machine in the hopes of gaining additional credential levels. We also say there's a 15% chance the attacker randomly selects a very low-level user machine on the network randomly to move to. This helps model randomness of how actually passwords can be found on the different machines, and that's our goal here with that. And then finally, after visiting the new machine, sometimes there could be additional credentials on that machine the attacker can exploit. We can say basically the attacker gains that machine's credentials at that point. So that sort of talks about the simulation framework itself, how the attacker moves across it, and then leveraging that simulation framework, we want to essentially quantify the network vulnerability. So essentially we can think of vulnerability as the risk of the domain controller being compromised by a lateral attack. And this is our goal, what we want to prevent from happening. So we can think of vulnerability as the definition of three components: network topology, the distribution of different user credentials, admin credentials, etc., and where the attacker is actually going to penetrate the network. However, in practice, we don't know the true credential distribution, and we don't know where the attacker is going to penetrate the network, leading to very difficult to actually come to actual conclusive vulnerability score. So here, our solution here is to actually use a Monte Carlo process to model this. So essentially we say we can simulate whether a network attack is successful from an initial penetration point, and then based on this, we can actually try many different scenarios. We can try many different penetration points, many different credential distributions on the network, similarly different kind of hygiene levels. And essentially these hygiene levels are how we're distributing these different credentials on the network. Are there many admin machines? Are there very few admin machines? So essentially we can say over many different trials with many different scenarios, we can get an aggregate score of the network vulnerability. And finally, the third component is actually identifying these at-risk machines. So you can think of this as many ways to defend, and we're going to talk about two different strategies, but there's also more uninformed strategies just based on the network topology itself. You can imagine things with high page rank, node degree. These could also be like more uninformed strategies. These are based on network topology, but also where the attacks are actually occurring. So these are like sort of more dynamic strategies that look at network topology and also where current strange activities are occurring. So the strategy one's more of a baseline, random anomalous neighbor, where we can say we can vaccinate neighbors of random anomalous machines. So we see an anomalous machine, we take some of its neighbors, let's monitor these. And then strategy two is something we developed called anomaly shield, which basically vaccinates machines with high eigenvector centrality that are near anomalous activity. And basically the intuition here is that we want to protect important machines in the network that are somewhat near strange activity. So this moves us up to more of the experimental setup. So that was sort of the technical aspect of it. So we actually collect data from three different networks, two Microsoft tenants, GS and GL, along with the Los Alamos National Lab dataset, GLANL. Here we provide some statistical information on the different networks we're looking at. We can see they range in size quite a bit. GS has 100 nodes and 200 something edges. GL is about 2,000 and 4,000 nodes and edges respectively. And GLANL is very large, having almost 15,000 edges and 14,000 nodes and 223,000 edges. When we look at average degree, we can see it's around 30, which is many times larger in terms of the connectivity compared to GS and GL. And that will be sort of important later down the line. So in order to quantify network vulnerability, we essentially took these three different graphs, we simulated different levels of hygiene, which means different kinds of credential access policies. We found a few interesting things, which we've color coordinated and highlighted. The first thing is that informed attack strategies lead to quicker attacks. That means once a user or an attacker has penetrated a network, the point from the initial penetration to compromise of the domain controller is actually much faster when they have a priori information on the network, which is not so surprising. We can imagine that knowing how the topology network would definitely impact the attack speed. You also find in orange here that improving hygiene reduces network vulnerability. So essentially the goal here is like if you reduce the number of admin credentials on the network, you actually would have a real impact on the vulnerability of your network. So it's better not to give out high-level credentials very freely. And then finally, networks that are more well-connected, as I pointed out before, GLANL had a very high average degree. And we see these well-connected networks are typically more vulnerable to lateral attacks themselves. And then the final component here is identifying at-risk machines. So essentially our goal is to monitor specific machines in the network in order to prevent the attacker from laterally moving. So we find basically in summaries that anomaly shield is a very ineffective general defense. If you don't know the network topology a priori, you also don't know where they're going to penetrate, where they're going to attack, or what kind of attack strategy they're using. Anomaly shield is a very effective defense to use. We also find that larger graphs in general require more informed defenses. So basically this means in very small networks, it's much less important how you're choosing your machines to evaluate for defense. But in these larger networks, you need some more informed defense strategies in order to better pick machines to monitor. And that makes intuitive sense. So that wraps up part 2, algorithmics. And then now we're going to move into part 3, databases. So basically in part 2, our goal is focused on the post-breach adversarial modeling mitigation. And now we're going to turn our attention to pre-breach adversarial detection and defense. We can think of this as basically in part 2 after they're on the network, and now before they're on the network. We're trying to prevent that from happening. However, even though we want to prevent these lateral attacks, current databases are actually very small, are not publicly available, making this actually very difficult to develop these strong next generation defenses. So essentially our goal here is to create these new databases to enable the next generation of malware detection models. This brings us into MalNet Graph, a large-scale database for graph representation learning. We're planning to submit this to NeurIPS in the next week here. It's a collaboration between myself, Yuzhao, Joshua, and Polo. So why MalNet Graph? Okay, so there's actually a few different motivations for this. And this actually will start with the number of existing limitations with existing graph classification databases. Many of the current ones are actually very small, containing relatively few graphs, small graphs in terms of the number of nodes and edges, and limited in terms of the number of classes. If we actually look here on the right, we can see how MalNet actually scales in comparison to all the different kinds of graph classification data sets used to date. We can see they cluster more on the lower left-hand side, and the only comparable cybersecurity database that looks at function call graphs, which I'm going to go into more, CGD, which is the other blue one right over here, is actually much smaller, having roughly around 1,000 nodes on average per graph, roughly around 1,000 graphs, and 2 classes. We can see that on average, MalNet has 17,000 nodes per graph, 1.2 million graphs, and 696 classes, so much larger in scale, allowing for better defenses to be able to be generated. So let's move into actually collecting the candidate graphs. We select the Android ecosystem for its large market share, easy accessibility, and diversity of malware itself. The collection process took about 1 month and 10 terabytes of storage, where we collect these Android APK files from the Andrew Zoo repository, an online APK repository for Android files. We also select files with both a type and family label. And what that means here is we can look at this figure on the right, and we can imagine there's 2 labels for each APK file. A type level label, which is a very high level thing, saying that this is like a worm, or we also have some very low level labels, such as the family, like what specific kind of worm is it? And then essentially we collect all this information. We also collect the raw virus total reports for each of these files, which is essentially all the raw label information that went into aggregate into actually selecting these sort of downstream, very pre-processed labels for the graph type and family. So actually processing the graphs themselves. So the first step is once we have the Android APK files, is to actually extract the function call graph from it itself. You can see an example one on the right here. These are actually directed graphs containing disconnected components and node isolates. And essentially we chose to store each of these in an edgeless format for its wide support, readability, and ease of use. It actually ends up taking about 443 gigabytes of disk space. So what can we do with this MalNet graph database? So we found there's actually some new discoveries that were enabled. So we saw that graph representation learning scalability and large class imbalance, there was actually quite large issues for a lot of existing techniques. We also find that simple baselines are surprisingly effective and that graph neural networks are not state of the art on this database. In addition, we find some new research directions are enabled, such as imbalance classification, explainable research, and class hardness. We'll go into each of these a little bit more in a second. But first, let's talk a little bit about the experiment setup and how we're going to evaluate all these things. So we split MalNet graph into a 70-10-20 training validation test set split. We can also create malnet tiny containing 5K graphs across 5 balanced classes, allowing for quick prototyping of different experiments. We also evaluate 7 state-of-the-art methods using macro F1 score, including 2 graph neural networks, a GCN and YIN, which is current state-of-the-art, and 5 data mining techniques, LDP, and some others. We've also trained each graph neural network using a hyperparameter search over the learning rate in hidden units. We want to make note that it actually took 26 days to complete this using the NVIDIA DGX A100, which is NVIDIA's most powerful graphics processing server they actually sell to the public. And then finally, each data mining technique has a parameter search over each method's hyperparameters, along with the random forest model downstream used to classify after using the graph representation learning techniques. So a little bit about the experiments. So we actually have 3 big takeaways here. And this table basically shows each method as a row, and then we have 3 different categories of columns. Type level classification performance with 47 classes, family level classification with almost nearly 700 classes, and then malnet tiny accuracy. So we actually choose accuracy since it's a very balanced classification task versus the type and family, which is quite imbalanced, which is why we go with a macro F1 score. And there's 3 major takeaways. Is that the first one is less diversity, better performance, which we can see color coordinated in green here, which makes intuitive sense. As basically you have 47 classes, it's a much easier classification task, whereas you move to 696 classes, it's much harder. And we can basically see when we jump to this increased diversity, performance drops. Also, we find that simple baselines are surprisingly effective. LDP here, along with no G farther down in the table, actually performs quite strongly, especially on the family level classification here with 696 classes. We can basically see that it's obtaining near state-of-the-art performance, but it's actually using simple statistical aggregate information on these networks, such as like average degree, standard deviation, just basic statistical properties. And finally, we find that graph neural networks are not state-of-the-art. This can be seen across both type and family, more noticeable in the family level in the red here. Basically, see that compared to LDP and Feather, it doesn't perform as well. And this is actually very quite surprising, especially considering the time component that it took nearly 26 days to train these models. And then finally, we can look at some of the research directions that are enabled, such as class hardness exploration. So if we look at this heat map here in the bottom figure, basically we see each method as a row and each malware type as a column. And the darker the color in each box, basically the better performing that method is at classifying that type of malware. So let's look at the orange column here, sort of in the middle of the figure. This is actually called malware Trojan. This is the type level classification. We can actually see it's not many classes. So this is actually ordered from decreasing class size. So the farther to the right, the less examples of this class that exist. And over to the left, there's more of them. So we see that actually this class is pretty well predicted by almost every method. However, if we go to the left where many more examples on the Troj and Adsware classes in green, we can see that these methods actually can't well predict on almost any of them. Any of the methods can't predict on this class. So this actually leads into some good motivation for exploring why certain classes are harder to predict than others. In addition, we can look at explainability research and ask questions like, why do certain methods outperform on different types of classes? So if we look in the red box here on the Clicker Trojan class, we can see that basically certain methods like Feather, YIN, and GCN outperform the other methods. And this leads us to the question to why do they outperform? So this could lead to interesting motivation to study when certain techniques might outperform on different graph structural motifs and what the reasons are for these different performance levels. So that wraps up malnet image, and then we'll move into its counterpart, or malnet graph, moving into its counterpart malnet image, which is a large-scale cybersecurity database of malicious software. So this will be my proposed dissertation work, and what I'll be focusing on in the coming semester. And this will be a collaboration between myself, Raul, and Polo. So why malnet image? Very similar to malnet graph, our goal here is to enable large-scale malware detection and classification research. However, that's actually not been available to the public currently. So if we look at the table on the right, the leading prior to this malnet development will be a malnet image, which only had 9,000 roughly images across 25 classes. Very small for any kind of deep learning research, or any kind of image classification research in general. And typically all the databases and data sets that are being published here are private, used by different kinds of industry leaders like Microsoft, Intel, and McAfee. We can see that while they're actually quite large, none of them are available to the public and not really allowing reproducible research. So our goal through Malnet Image is to enable this kinds of malware classification research to go on in the light of the public. So the first task here is to construct Malnet Image. This begins by collecting the candidate images. We can reuse the Android APK files downloaded from the Android repository for Malnet Graph. And the benefit here is we'll have the one-to-one match with the function call graphs for Malnet Graph, meaning each image will match a function call graph. Essentially, now that we have the Android APKs, we have to do different pre-processing steps. In order to process these APK files into an image representation, there's a couple things we have to do. First, we have to extract the DEX file from each Android APK, which we think of as sort of like the executable bytecode of the APK package itself. And then once we have the bytecode, we can convert it to a 1D array of 8-bit integers, and then we can convert this 1D array into a 2D array, very similar to the image we're going to see on the right-hand figure now. And the final step is to code different kind of RGB color-encoded channels, which represents different kind of structural semantic information of the file itself, which corresponds to what we see on the Android APK structure, the header, the strings and identifiers, and the actual data. And we can see how this color coordinates into the image over on the right there. Task 2 then will be to benchmark different techniques. Our goal here is to evaluate numerous malware detection classification techniques that have previously been studied. However, they were on private databases or a very small scale ones like Malimge, which we previously discussed. And our goal here is basically by benchmarking all these techniques to provide a state-of-the-art baseline for future work. So our goal here will be to evaluate things such as semantic information encoding via the color channels, test various deep learning model architectures, look at model pre-training, where it's been shown that natural training on natural images actually has a benefit for malware detection, and finally look at different kinds of imbalanced classification techniques, because Malnet Image is actually quite an imbalanced database. And then finally, in task 3, our goal will be basically to evaluate malware detection capabilities. So we want to look at different kinds of we want to enable the first large-scale reproducible experiments, providing both data and implementation of all these methods. And the goal here is to provide strong baseline results to compare the next generation malware detection techniques for both detection and classification levels. So that wraps up part 3, databases here. Now we're going to move into part 4 of the dissertation, which is models. So we find that basically having access to large-scale robust data doesn't necessarily guarantee model robustness, and therefore we also need to develop robust models. Specifically, in this part of our dissertation, the goal is to tackle 2 high-impact problems in cybersecurity and healthcare affecting millions of lives through the lens of robust deep learning models. And this brings us to the first work, Unmask, Adversarial Detection and Defense Through Robust Feature Alignment. This was presented at IEEE Big Data 2020. This was a collaboration between myself, Shang, Polo, and Jay. So let's bring us to a high-level motivation overview of the Unmasked work. So the goal here is basically protection via robust feature alignment, and we'll talk about what that means exactly. So on the left-hand side here, we see an image of a bike, and to the human eye, it looks just like a bike. However, with small modified pixel perturbation to a deep learning model, this will actually look like a bird. We can see this on the bottom side of the figure, where we see this vulnerable CNN model actually takes this image and misclassifies it as a bird shown there. However, when we say it's classified as a bird, there's actually some semantic information we expect a bird to contain, like we expect a bird to have a beak, feathers, tail. However, when we run the same image of this, attacked bike that looks like a bird's model through an object detector, we can actually extract the robust, human-aligned robust features. This can be things like the wheels. So when a human sees this, they see the wheels, the frame, the handle, the seat. And we can think of these as the robust features of the image. And what we find is basically that we can extract the robust features of the image because they're not being attacked. It's the whole level image classifications that are being attacked. So the object detector allows us to extract these features, allowing for a form of defense. So we can compare the features of the expected classification of the bird with the extracted features and see there's no overlap. And this would be a great indication that there's actually an attack going on, which allows us to rectify the attack by saying what's the most similar class to the robust features extracted, and then rectify that kind of attack by reclassifying it correctly as a bicycle in this case. So this leads us to the notion of robust features applies a robust model. So this actually leads us to a motivation for why it can be good to actually have two models, one for classification and one separate for defense. So what's been found is that robustness is actually a function of the data itself. So adversarial examples can be attributed to non-robust features in the data. And we can think of these non-robust features as something like the human eye typically wouldn't notice, but that's pixel patterns in the image that the machine learning models can train on. And these non-robust features are actually quite predictive, but they're just not human comprehensible. And it's been shown that basically training only on robust features significantly lowers the benign accuracy. And that provides a good motivation for why I want a separate model classification pipeline separate from the defense potentially. So essentially using these images robust features, and here we can see the bike, we can see like the wheel, the saddle, the handle, and these would be considered segmentation masks on the image. And basically this will form the bike's robust features, and the benefit here is they're human comprehensible, and this will form the foundation for our adversarial defense techniques. So the first step is to extract the robust features and attain these different kinds of robust features from each image. In order to do this, we use a mask RCNN model trained on segmentation masks. That's very similar to the one previously shown. There's one mask per robust feature. The dataset has 44 robust features. And for example, that could be like the bike as previously shown, and the robust features would be the wheel, the seat, and the frame. And then a little about the experimental setup here for the datasets we use. So first off, we have to actually train the object detector to extract these robust features. And here we use the Pascal part dataset, which has these nice segmentation masks on each of these images. Then we have to train the vulnerable CNN models themselves. We also use the Pascal VOC dataset, which has a nice correspondence to the Pascal part dataset. We also collect some additional data using Flickr, because we actually find the Pascal VOC dataset is a little bit small for all of the kinds of experiments we want to run. So we augment it and download some additional data. And finally, we have to actually do the detection and defense experiments. And basically, we have a matching between the Flickr and the Pascal VOC classes. Our goal here is basically to evaluate how well the defense works on this data. So a little bit about the evaluation. We look at 4 strong adversarial attacks, projected gradient descent, and an MIFGSM. And we get different levels of feature overlap. And basically, the idea of feature overlap is if there's 3 classes, there's actually, if you mix and match different classes, you can have different amounts of overlapping features. You can imagine thinking like a dog and a cat will have very similar features, even though they have different classes. However, a car and a human are going to have very different features and very little feature overlap, even though they, it's only 2 classes addition. So essentially, our goal here is to test the effects of not only the classes, but also the number of unique features in this class sets. So in CS3A and CS3B, we have 3 classes, but the number of actual unique parts varies, changing for different levels of feature overlap. So essentially here, our goal is to begin by detecting attacks. That's the first step. So our goal here is to evaluate the detection of adversarial images that have been perturbed and modified. And we do this in a 50-50 ratio of benign to adversarial images. And basically we find here is that low feature overlap equals better performance. And this is not too surprising. If the features of these images are distinct, we can actually better represent what the actual true image class is. And sometimes this can actually be more important than the number of classes itself. So if we look on the ROC curve on the right here, we can see CS3A in dark blue on the top, and then CS3B in the light blue much lower to the bottom. And we can see the effect of feature overlap here quite sharply. When there's low feature overlap, roughly 7%, we have a very strong detection curve, whereas in the light blue, when there's high feature overlap, it's much harder for the defense to distinguish the attack. And then once we actually detected the attack, we might want to counter the attack. And there's a couple key things we find. Again, less feature overlap, better performance. And then we also find, which we don't show here but discussed in the paper, is that performance is independent of the architecture it's defending. One nice benefit. And then also a little more about the countering attacks. We also find that comparing to state-of-the-art gold standard adversarial training, LMAS can actually significantly outperform no defense and outperform adversarial training across different class levels. This brings us into the final paper of the dissertation, REST, which is for robust and efficient neural networks for sleep monitoring in the wild. This is a collaboration between Raul, myself, Kao, Jimeng, and Polo. And this work was presented at the web conference, previously known as WWW. So let's begin a little bit of motivation and the importance of sleep diagnosis itself. So essentially, it's imperative to develop accurate and efficient sleep assessments. And we can see this based on this figure below, where we can see that in the United States alone, $411 billion is the estimated impact of sleep disorders. So let's talk about a little bit about how sleep diagnosis works in general. So typically on the bottom left-hand side here, you're going to go to a sleep lab, you're going to be hooked up to a bunch of things and stay overnight, and they're going to monitor you, they're going to take some vitals, and basically they're going to run this through a deep neural network to generate a hypnogram. However, this process is costly, invasive, inconvenient, and many people don't want to go through it, leading to undiagnosed sleep disorders. Alternatively, at the top, you can do this at home, maybe using a Fitbit, an Apple Watch. However, there's a lot more noise in the home environment, and also you have to think about energy efficiency, and that these models aren't using all the resources of the phone or whatever device you're using. Typically have very low power profiles. But the same idea applies. You're also going to monitor at home, and you're going to run it through a deep neural network, generate this hypnogram, which is then be analyzed by a team of doctors to write a final diagnosis. However, there's key challenges in enabling this at-home deep learning model to work for sleep monitoring. And the first challenge here is susceptibility to noise. So essentially, in order to make correct classifications, state-of-the-art models currently only work in pretty much no noise environments, basically the sleep labs. And this can be seen on the figure on the left here, where at the bottom we look at an expert-scored hypnogram, and we can see that in the no noise environment, the state-of-the-art model at the very top works pretty well at classifying. When we add low levels of noise like Gaussian noise, medium levels, or even high levels, we can see how performance starts to degrade with increasing environmental noise. And this won't work in many home environments, that means. And also a second key thing to consider is the latency and energy usage of these different models. So current state-of-the-art models might take up to 5 minutes to classify, and quite a few joules to do this classification process also. And our goal here was we want to minimize both the time and energy usage. These are very power-constrained devices potentially that will be doing this monitoring on. This brings us to the REST process itself. Here our goal is to develop neural networks for at-home sleep monitoring by generating models that are robust to noise and energy and compute efficient. So essentially there's a 3-step process here for the at-home sleep monitoring to enable this. So to develop these robust and energy efficient models, we actually train models using adversarial training with spectral regularization and sparsity constraints, and then we can prune the model, downsize it, and finally retrain it using adversarial training and spectral regularization. And this essentially will allow us to develop the REST process to develop these noise robust and energy efficient models. And once we develop these models, we can evaluate them on 2 different very large popular data sets, Sleep EDF and SHHS. There's some different little historical notes about them. Sleep EDF was collected more in the home environment, so it's more noisy, whereas SHHS was collected in a sleep lab, so it has less noisy data. In terms of the metrics we use itself, when looking at noise robustness, we look at the macro F1 score, since this is actually a pretty imbalanced classification task. We also look at efficiency, looking at the flops, the inference time in joules, which we measured on a Pixel 2 smartphone. So looking at the results themselves, particularly for noise robustness, we see that REST models perform well in noisy environments, which is the goal that we set out to do. In the top row, we see a state-of-the-art model in the green in a no-noise environment, and we can see as we increase noise, performance drops significantly across different types of noise. However, when we go down to the bottom row and look at REST models, we can see that actually the accuracy is maintained even in these high noise environments, which is the goal. We can also further look into the different kinds of performance at a per patient hypnogram level. So that was a very high aggregate statistic we looked at before, and this is a much more finer grained resolution to see how this performance actually might look. From the top here, we see the expert scored hypnogram. In the middle, we see on the left the state-of-the-art model. On the right, we see a REST model in the no-noise environment. And the big takeaway here, as we look down at the different levels of noise in the bottom, is that the accuracy of the hypnogram persists with increasing levels of noise in REST, whereas with the state-of-the-art model, the hypnogram classification process begins to fail. And finally, when looking at model efficiency, we see that we evaluate performance on the Pixel 2 smartphone, and we can see that REST-trained models are approximately 9 times faster and also use up to 17 times less energy. And this is critical, like we said, when using embedded devices or like those low energy profiles only available. So in conclusion here, today I presented my PhD dissertation plan, comprising both the completed and proposed work. The dissertation was comprised of 4 major components: the tools that guide and assist researchers in navigating the complex field of graph robustness, and then through the tools developed there, the algorithms, and also the databases and the models. So in summary, thank you everyone for being here, and this is the end of my presentation.
Okay, thank you. Thank you for presentation. And now we can take questions from the audience. And then after the audience question, then we'll kick the audience out so that we only have the community left. So yes, so any question from the audience for Scott? You can either type in the chat window or you can unmute yourself. Yeah. Okay, no question from the audience. I think then we will have the question from the committee. And before doing that, then Scott, I'll ask you to stop the recording.
Okay,
And
let me do that now.
Yes, and also